Thank you. Okay, yes, it's working. So I also would like to thank the organizer for the invitation to talk here. It's always a pleasure to be back in Trieste. And I will talk about gravitino and decaying dark matter at LHC. It is work based on collaboration with many people. You see them written here: George Arcadi, Federico Dradi, Marco Nardecchia, Alexandra Albray, Marco Battaglia, Jasper Azenkamp, and Fazila Mahmoudi. So I will try to cover everything. It's a little bit, well, a lot of material. We'll see how much I get through. So I will start to give us a short introduction, trying to convince you that apart from the WIMP mechanism, there is also other mechanisms which can produce the dark matter in the right abundance, and they can give you also rise to an interesting phenomenology. And then I will go and discuss two scenarios of this kind. One is connected to the gravitino. The gravitino, of course, has a kind of a very interesting and very special role in theories with supersymmetry, since it is the gauge fermion of supergravity, and it is in some sense a particle which has also a characteristic which are just determined by the symmetry. And so it is in some sense one, I think, of the supersymmetric particle which is really very interesting to explore. And I will discuss here different scenarios of gravitino dark matter and their phenomenology at the LHC. In particular, in the case of stop NLSP, what happens instead if you have a neutralino NLSP in the PMSSM. And then, if I have time, a short connection to the case of baryogenesis in the case of gravitino dark matter. And then in the last part, I will instead move to a scenario which is not supersymmetric, and it's a very simple scenario which we wrote down in some sense to try to capture the basic ingredients of this connection of FIMP and super WIMP without having a full model, if you want, a full ultraviolet complete model. The characteristic of this model is that you have very minimal set of parameters, and you can nevertheless also explain the dark matter density and have also interesting phenomenology. Okay, so let me start with this introduction and try to convince you, indeed, that we have actually something more interesting, or at least as interesting as the WIMP to study. And this is practically the idea of the super WIMP or the FIMP paradigms. And the idea here is, in some sense, to try to produce the dark matter, not from thermal equilibrium, but from a particle which used to be or was in thermal equilibrium. So the classical picture is that you have a WIMP, and the simplest scenarios are where you just add a small decay channel of the WIMP into some other particle. And the WIMP, of course, can decay into this particle while it is still in equilibrium, so in this period. And at the same time, it will decay then eventually after it freezes out. And in these two very different epochs, it will at the same time produce the particle, the daughter particle in the decay. And these mechanisms are usually called FIMP in this equilibrium regime and super WIMP in the final regime. Notice that in this case, these two mechanisms in some sense are both present if you have a particular decay channel. And the characteristic to be in some sense very, they are effective, especially if you have very small couplings, so that the decay time is actually very long. And we will see, therefore, also later, that this is usually connected to a particle with a long lifetime. Now, which one of these two mechanisms actually dominates in the production of dark matter depends on the parameters. Here, for example, we are changing the mass of the heavy field which decays. And this, as you see, depending on the mass, you could have either the super WIMP contribution dominating or the FIMP contribution dominating. And in some sense, both of them can actually give rise to the right density to have a dark matter, the right relic density for dark matter. So, and as I said, they are actually connected always, they can be connected to the same coupling, and therefore they are in some sense usually present at the same time in a particular model. Now, what does this have as consequences for phenomenology? Well, of course, it has it changes in some sense the WIMP connection that we are usually used to something like a FIMP or super WIMP connection. So in that sense, there you would have still this early universe production from a WIMP in some sense with this leakage into dark matter that I just talked about. But at the same time, you can use the similar diagram to get phenomenology at colliders or in indirect detection. At colliders, again, you can produce this mother particle, this which I call here WIMP. And this, as I said, will actually result usually to have a long lifetime, and therefore bring about displaced vertices or even metastable particle at the LHC that you could try to measure and to disentangle what is this decay length. On the other hand, the dark matter in these scenarios is coupling very, very weakly because this is actually very, very slow decay. And therefore, in general, you don't really need a symmetry to make the dark matter stable. You usually have naturally dark matter particles with lifetime which are much longer than the age of the universe. Actually, we will see later, we have lifetimes of the order of 10 to the 28 seconds. And this means that, well, if you are lucky, the dark matter particle could decay actually now in our galaxy, and you could be able to observe the decay products of the dark matter decay. And this, in some sense, will also give you another information on, of the dark matter couplings to the visible sector. And in the simplified model I will talk at the end, it's actually these couplings are related, and therefore you can really also cross-check and, in some sense, try to measure all the parameters of the model. Now, the decaying dark matter is actually more general. So here is just my usual plot to show you what is the flux that you would expect from a decaying dark matter candidate. It is, of course, proportional to the density instead of the density square. And the decay rate depends, of course, on the lifetime of the particle. Notice here, again, the spectrum. The spectrum, in some sense, can be the same spectrum you would expect also for annihilation. And in particular, you could also have lines, and we will get perhaps to that at the end. And if you have lines, the advantage, of course, is that it's a very smoking gun signature on one point. And secondly, the position of the line will tell you immediately what is the mass of the dark matter. So let me go now to the case of the gravitino. The gravitino, of course, has a long history, and it has been studied in cosmology since many, many, many years. And the usual thing is actually that is very famous is the so-called gravitino problem. And the gravitino problem, well, I will actually talk to it in the next slide. But the point is that usually the gravitinos, if it is not stable, it is very long-lived, and this can cause troubles in cosmology. But assuming it is stable, the densities of gravitinos can be set both by equilibrium computation. So in the case of the equilibrium density, you get that the gravitino couples usually very weakly, and the couples when it is still relativistic, so that it has actually the right density at the corresponding to masses which are very small, and therefore it's usually a warm or even hot dark matter, which is now more or less excluded. And this one was discussed in the 80s already. It was actually, I think, the first supersymmetric dark matter candidate discussed. And of course, so this scenario is actually nowadays not the best scenario from structure formation. And therefore, we will concentrate on the second scenario where you have the gravitinos never in thermal equilibrium, but you produce them slowly, both through this FIMP and super WIMP mechanism I discussed before. But actually, in the case of the gravitino, you also have dimension 5 scatterings, which gives you also a contribution which is proportional to the heat temperature. And depending on the heat, how large the heat temperature is, this is actually very often the dominant contribution. If you see here, this is, for example, in this case, the one part of the contribution is coming from the gauginos. So here you have a dependence on the gaugino masses square and inversely proportional to the gravitino mass. And this will be important later on in the discussion. So through this production, you see that if you have reheating temperature sufficiently large, you can produce, in some sense, the right number densities for masses of the superpartners in the GV-TV range. Now, the problems I was talking about is actually here. It's the fact that if the gravitino is not stable or not very, very long-lived, as we will discuss later, if you just, it is not the LSP, then it can decay into other supersymmetric particles with a lifetime which is long. It is of the order of 10 to the 7 seconds, for example, but not long enough. So 10 to the 7 seconds is actually after nucleosynthesis, and well, it's approximately 1 year if you want to translate that. And if you have a large population of gravitino decaying after nucleosynthesis, this can actually destroy the abundances of light elements and well, destroy the predictions of nucleosynthesis. And from this plot, you can see some of the limits you can pose in the scenario, depending in this case, again, on the reheating temperature, exactly because the density is here assumed to be proportional to the reheating temperature. And it turns out that if you want to be completely safe, you have to really have a very heavy gravitino above something like 40 TeV, or otherwise you have to live with a small reheat temperature of the order of 10 to the 5 or lower. So in that sense, these changes, if you want the cosmology, the presence of gravitino, which is not the LSP. In the scenario I was discussing, instead, I will take the gravitino to be the LSP, and I will then have the limits on BBN not on the LSP, which is in some sense either stable or sufficiently stable not to decay during nucleosynthesis, but on the NLSP. And this NLSP will be, in this case, for example, in the first study, actually the stop. We will take the stop as the NLSP for two reasons. One, of course, it is the fact that you have naturally a very low density of stops in the early universe because it's a particle which interacts strongly. And therefore, you are hoping that the limits on BBN nucleosynthesis are actually weaker because you have a low density. On the other hand, you have also, you probably all know, for naturality reasons, a light stop it's actually preferred by the in order to have a light Higgs. So in this case, of course, it will be the lightest stop. The other one can be much heavier. Now, in this scenario, we have looked at the BBN constraints. And there are still a region which is excluded by BBN, also for the case of stop. Even if the density is very low, you have actually bound state effects which cause actually a change in the abundances of light elements. And therefore, you see the regions here above is actually excluded because the lifetime of the stop would be too long. It's of the order of 100 seconds or so. On the other hand, if you want to have the right density of gravitinos, you have actually to be more or less on this line, depending on the reheat temperature. So in this plot, I'm taking something like 10 to the 7 GeV. And you see, therefore, that you have just the white region where if you are on the yellow line, you are exactly at the right density. And in the white region, you would be below the density. But of course, changing the heat temperature, you can move the yellow line about in this plane. And of course, lower heat temperature would move the line down and allow you to have also lower gravitino masses, which are in the other axis. But in general, at a certain point, this yellow line will cross in the practically red region here. And this one is actually telling you the maximal reheat temperature you can actually have. And this is plotted here. As you see, you are in the range of 10 to the 7 GeV or so before you really hit the BBN constraints, also for a stop NLSP. Notice that these bounds are actually avoided if you just switch on a small variation of R parity. And this is also the other scenario we will discuss. This was observed a few years ago. So if you have a small violation of R parity, actually with couplings in the region between 10 to the minus 12 and 10 to the minus 6, you are actually in a region which cosmological is very favorable, because on one hand, you can avoid these BBN constraints because the NLSP decays before nucleosynthesis. On the other hand, if the coupling is sufficiently small, you don't practically increase the washout processes, which would, for example, erase the lepton number or the baryon number, depending on which is in some sense, the mechanism you choose for baryogenesis. If you do it, of course, at a higher temperature and you have still washout processes active, you would actually erase this baryon asymmetry. So you see that you have small couplings, but not incredibly small. And in this case, of course, you would have that the NLSP would not decay into the gravitino, but would decay preferentially through R parity violation. So, well, of course, if you have a decay at R parity breaking, not only the NLSP decays, but also the gravitino decays. But luckily, the decay is suppressed by the small R parity violating coupling and by the Planck scale. And therefore, actually, you get very, very long lifetime. And there are already bounds, in particular from antiproton, which I'm showing here. This is one of the recent bounds, but given by De La Haye and Grefe a couple of years ago. from the antiprotons, and you see that this is the bound which constrains actually this R parity violating parameter to be of the order of 10 to the minus 9 or so. At lower masses, here's a large gravitino mass. At lower masses, the Fermi constraints take over, and they are of the similar order of magnitude. So this means, again, that this R parity violating parameter has to be small. Okay, so in general, then we have to study the two scenarios. We can actually study two scenarios at the same time. One scenario where you have conservation of R parity, and then this NLSP would decay in gravitino and top. And you see here the lifetime, which is quite long, 19 seconds for this parameter chosen. But of course, we have also the other choice to have a small R parity violation. In this case, the decay of the stop will be in bottom and a charged lepton. And the decay is a little bit smaller, so if you want, the lifetime is a bit shorter, but not very short. 10 to the minus 4 for collider purposes is actually very long lifetime. And this means that in both these cases, you actually expect not prompt decay and either displaced vertices or even metastable particles, in particular in the R parity conserving more metastable particle. And this means that the usual searches which has been done, apart from the metastable particle search, which has been already performed, do not really apply. So you have to do a dedicated analysis. And this is, for example, just the picture. What we did with Federico Dradi was to try really to see where does this stop decay once you produce it at the LHC. So we generated the events with MatGraph, and we actually simulated also the decay and the decay length. And as you see, you can actually have, depending on the lifetime decays, all are in your possible places in your detector. In particular, we will concentrate to look what happens when the decay are in the pixel or in the tracker, because there we can see the tracks more easily, and in some sense you would see that there is a kink in the track or even a vertex. And the other thing we will also consider is the case where the decay happens really outside to the detector. And then in this case, of course, a stop, which is a charged object, could actually hadronize into a charged hadron and leave a track through the whole detector. So this is also a case where you could see something. And what we did here is to explore in the parameter space exactly what is the region which is accessible by the LHC searches. And here is this plot. We are plotting just the mass of the stop and the lifetime of the stop. So these plots actually apply to any scenario. So at the moment, we are not specifying what is the decay channel. And you see exactly, we are requiring practically that a sufficient number of events, of decay events, either in the pixel, the tracker, or how many, at least some events outside the detector. And as you see here, in the green line actually gives you the curve which corresponds to 10 decays outside. So above the green line, you have more than 10 decay inside the detector. Sorry, outside the detector. Instead, the red and the blue line correspond to tracker and pixel, respectively. And below the line, you will have more than 10 decay events, either in the pixel or in the tracker. So as you see here, if you want to cover the whole range of lifetime, you need actually to combine both searches, metastable particle and pixel or tracker, the displaced vertices. And you have also a region, which is here. We will have it also more often later, a region where you could actually do both measurement, have both displaced vertices and metastable particle. And in that region, in some sense, you would have the hope to have the better lever arm to measure the parameters. Notice here in yellow is the region which is already excluded by the present searches on metastable particles, which, of course, is very effective for very long lifetime, but it runs out of steam when you have shorter lifetimes. Yeah, so this one, of course, you can interpret in both models, either in the R parity conserving or in the R parity violating model. And here it's the parameter space, in the first case, gravitino mass and stop mass. In the other case is R parity violating coupling and again stop mass. And you see again that here, of course, in the case of the R parity conserving, as I was saying, for high reheating temperature, you are actually mostly in the metastable particle or a metastable signal region. Instead, in the case of the R parity violating, you have actually regions which is also only covered by the displaced vertices here above. in some sense, this is the limit from the indirect detection of dark matter, which of course depends, one has to say, on the mass of the dark matter, so on the gravitino mass. So here we have taken 1 GeV, so depending on the mass, you can move it a little bit around. But for this parameter, you see immediately that there is a region where you need actually displaced vertices in order to cover the whole parameter space that it is available. Now, these ones are actually, I will have to stress, they are for the ultimate limit of the LHC for 3000 inverse femtobarn, so not really at the next run. Now, of course, the best hope would be if you really have a displaced vertex inside the detector, especially in the tracker or in the pixel, then you would also be able to see the decay, the tracks, and measure probably the momenta of the decay particles. Notice that in the two decays, the visible particles are the same. It's always a bottom and, well, yes. So the visible particle are always bottom and lepton, and these ones are invisible in this case, and in this case it's just a two-body decay. So in some sense, from the particle point of view, you would see the same thing in the final state, but of course the missing energy will give you a hint, and I hope I don't have to ask you which of these two is the R parity conserving and which is the R parity violating distribution of momenta. So I think it's pretty clear. This one is actually the two-body decay, and this one instead is the four-body decay. So if you would be able to measure the momenta, you would actually be able to really to distinguish if you are R parity conservation or R parity violation. Okay, so let me go now to the other scenario, the scenario where we studied the gravitino in the PMSSM. This was work done in collaboration with Arbey, Battaglia, Hasenkamp, and Mahmoudi. And in this case, we wanted actually to ask especially the question, what happens if the NLSP is a neutralino? And can you really distinguish or see any differences between a neutralino dark matter and a gravitino dark matter with neutralino NLSP? So we took for the moment the R parity conserving PMSSM. PMSSM is a phenomenal MSSM with 19 parameters plus 1. So this plus 1 is the gravitino mass in this case. And we've imposed also a lot of the constraints which are already there from low energy observable flavors and also LHC, SUSY searches, and monojets. And the first thing you can notice immediately is actually the composition of the neutralino NLSP. The composition here is given in Higgsino, Bino, and Wino, and as you see in the case of gravitino LSP, you don't really care what is the composition of the neutralino. You have actually nearly one-third, one-third, one-third in all the three different types. Instead, if you require the neutralino to be really the dark matter, and you want to produce the dark matter density through the WIMP mechanism, you are actually nowadays constrained to be mostly in the Higgsino region. And this is just because the limit of LHC have excluded most of the Bino space. And so you have some regions where you can arrange to have the right density with Bino, but most of the time, actually, you are in the Higgsino region and very, very rarely in the Wino region. So in this sense, you have really a completely different composition of the neutralino in the two cases. And this, of course, gives you also differences in what you expect. Here is one plot where we try to compare with the signals in direct detection of dark matter. So in this case, it's the gravitino case. This one is the neutralino case. In this case, of course, gravitino is the dark matter. So this signal is actually not there. So even if you see points which are above the line, you shouldn't care because the gravitino you cannot see in direct detection. But you notice in the color is instead what can be excluded by LHC, at least in fraction of points. So you see that the LHC would actually be very sensitive to the blue point and the dark blue in particular, and will exclude mostly the light, if you want, NLSP mass. This instead is the case where you have really imposed also a constraint that the neutralino makes up the whole dark matter. And that you see immediately in this case, you have actually that you have some kind of limit of the cross section. You cannot go very much lower. Instead, in case of the gravitino, you can actually be all over the place in this case. Of course, the way to disentangle the two would be to have a signal where the parameters look like be already excluded by the direct detection. And this will already tell you that the neutralino you're seeing at collider is not really the dark matter. Now, the other important thing is the production of gravitinos. As we have seen, the production of gravitino is mostly dominated by the reheat temperature and also by the spectrum of the particles and the gauginos in particular. And this one is actually shown in these plots where we, first of all, these is are the points which are already more or less excluded by the present searches, and this one would be in the next, they run at 14 TeV with 300 inverse femtobarn. So we see here, we are plotting here the, logarithm of the reheat temperature. Sorry, no, that's, as a function of the mass of the NLSP. So in this case is the, again, always the neutralino. And we see here clearly that the, we have already some constraints, but there are actually also white regions at very small neutralino mass. So therefore, that is still a possibility. And on the other hand, in the future, we will be able to exclude neutralino masses, at least, depends how well, but even in these dark blue regions, you exclude 80% of the points up to 1 TeV, more or less, of the neutralino mass. Here, what I wanted to show you is that, in principle, you can have gravitino dark matter for any reheat temperature, as you see here. There are blue points all over the point. The high reheat temperature points are here, and they are actually more easily tested by LHC, because in that region, in order to have high reheat temperature, you need low gaugino masses. If you remember the formula, it was proportional to the gaugino masses square and the reheat temperature. And on the other hand, you have also regions where the reheat temperature is very small, and in this region below here, actually the superwind mechanism is instead playing a role in the production of gravitinos. And due to this connection with the gravitino mass and between the gravitino energy density and the gluino mass and the reheat temperature, we can actually say that the next LHC run will be able to probe this high reheat temperature region and possibly exclude reheat temperature of the order of 10 to the 9, 4 10 to the 9, or something like that. So this one is the gluino mass, which will nominally be probably excluded in the next run, a little bit below 2000 GeV. And as I said, these are the curves which give you the lowest gravitino mass, which is still compatible with the energy density of the dark matter. Okay, so let me go to the baryogenesis connection. The idea here is, of course, since we have our parity violation, then the one idea could be also to try to do also baryogenesis with it. And actually, the idea was already a few years ago by Sandram Covi and Covi later. And the idea would be to produce the baryon asymmetry through, in this case, the B-violating coupling, R parity coupling, and the decay of a BINO, which is freezing out, in essence, after he's froze out. These are the diagrams which contribute to the CP asymmetry. And in order to have a non-vanishing CP asymmetry, you need usually a supersymmetric particle lighter than the BINO. In this case, it is the gluino, which is here. And you have practically to consider this scenario. In this scenario, you can very easily embed also gravitino dark matter through the same decay. And this is explained shortly here. The idea, of course, is that when you produce the baryon asymmetry from the density, for example, of the BINO, you have a large suppression coming from the epsilon CP, which is a small number. In the case of dark matter production, you would get a large suppression in the case of gravitino, especially because the branching fraction of decay into the gravitino is very small. And in this scenario, it's not difficult to get an epsilon CP of the same order of this branching fraction, so that in some sense you are able to explain the order of magnitude equality, or if you want, a similarity between the density of baryons and density of dark matter, just by assuming that these branching fraction and epsilon are of the same order. Notice that at the end, this ratio is independent on the mother particle density, and you just need to have, in some sense, the right epsilon CP and the right branching fraction. Unfortunately, the scenario is not as simple, and this is because there are also washout processes. If you look at things more in detail, as we are still doing, you get a lot of contribution and effects from washout that actually moves the scale, especially of the scalar particle, to quite a high scale of the order of 10 to the 7 GeV. So the scenario is still working, but you need larger masses of the scalar particle, larger masses of the BINO, which is also beyond the LHC, if you want, will ever probe. And in this scenario, we'll also have the possibility to have the right dark matter density, but again, due to the suppression through the large scalar masses, you need also to push the gravitino mass high. Sometimes it's not surprising, all the scales goes up, so it could also be natural to have a heavier gravitino, and you can go also to 1 TeV or 3 TeV gravitino. In this case, the one good news is that the gravitino lifetime is in the ballpark what will be tested by AMS, especially because in this case, the gravitino would decay also in antiprotons through the R parity violating coupling, which is also baryon violating. Okay. Oh, I have 0 seconds. So I show just one plot on this. So we will look also at this more simple scenario where you have just 2 couplings and 2 masses to parameterize actually this mother particle and daughter particle. So the dark matter here is psi, and sigma is the particle which produces the dark matter. And in this case, you can have, of course, the decay of the dark matter again, and you have actually a possibility to have both indirect detection and production of dark matter in the right ballparks with coupling of the order of 10 to the minus 11 or so. And we tried to look at what are the prospects for detection at collider. And what we found is, again, that is the same picture as with the stop. You could produce it and, in principle, have both displaced vertices and the metastable tracks. And there is still also room to have this double detection, both in displaced vertices and metastable. But, of course, the indirect detection constraints, depending on the dark matter mass, are, in some sense, cutting off part of this region. If you would be in this region, you could be able, probably, to measure both couplings, the mass of the dark matter, and possibly also the mass of sigma. So in that sense, in this case, that would be the best case scenario where you could be able to reconstruct the full model. Okay, so I have to finish. You can also explain the line, but I don't want to spend time on here. The line, in case of the line, you don't have displaced vertices, but prompt decay. And here I leave you my conclusion. Since I ran out of time, you can probably read it yourself. I hope I convince you that there are, in some sense, alternatives to the WIMP mechanism. Thank you.
Time for a couple of questions. Yes, no. Oh, yes.
If supersymmetry will be discovered at LHC, what can you say about the mass of gravitino and how it is related to the vanishing cosmological constant if we see this picture in the cosmological setting?
Well, I mean, the gravitino mass is, in this case, scenarios is not directly measured at the LHC. So in this case, you would measure only the NLSP. Only if you are able to also measure the decay, the lifetime, and you are sure that is an R parity conserving case, then you would get a hint of the gravitino mass.
Yeah, I do not mean the measuring, I mean the theoretical conclusion of discovery. What would it imply for gravitino mass? What are options?
Well, I mean, of course, as you all know, it depends, of course, on the mediation mechanism, what is the size of the gravitino mass. And in this scenario, we are not looking at a particular scenario, a particular mediation mechanism. We are using just the gravitino mass as a free parameter. As you see from the plots, usually we are looking more at GeV or 100 GeV mass of the gravitino, which seems to be the region where you can have higher heat temperature, which in some sense we like from the perspective of cosmology in order to have also the leptogenesis or baryon asymmetry production. But in these scenarios, you could also live with smaller gravitino mass as long as it is heavier than 100 keV, so it is sufficiently cold dark matter. You would actually, from cosmological perspective, be fine.
So you will need some mechanism of mediation which is compatible?
Yes, yes.
Thanks.
Okay, if there are no more questions, let's thank the speaker again.
Thank you.